Hello everybody. So, today's lecture, we are going to talk about graphing higher order polynomials. And all higher order means is pretty much any polynomial with a degree bigger than 3. Okay, and in addition to that, we're going to touch upon the topics of end behavior, the leading coefficient test, and then we'll talk about zeros of polynomials. So, let's go ahead and get on into it. Okay, so just to review, right? If we let an all the way down to a0 be real numbers, and we have the condition a sub n is non-zero, then we get to call the function f of x equals a sub n times x to the n plus blah 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 plus a sub 1 times x plus a naught. We call this our generic polynomial function of degree n, right? And the degree is coming from the highest exponent and has leading coefficients a sub n, which is just the value being multiplied to the highest degree variable. So that's our polynomial function. That's what we mean by polynomial function. And what we're going to talk about today are the graphs of these types of functions. So when it comes to graphs of polynomial functions, we get to make these statements. All graphs of polynomial functions have these two defining characteristics. The first is that all graphs of polynomial functions are continuous. What does it mean to be continuous for a graph? Basically means nowhere is there any breaks in the graphs. So no breaks. So, for example, here we go. Here's an example right here. This graph right here is an example of a continuous graph. It is smooth throughout. Nowhere is there a break in the graph. It is continuous. And on the other example, this is a non-continuous graph. Right? So why is that? We have a break right there. So there you go. So, in general, you get to make the statement that all polynomial functions have continuous graphs. There is no breaks in any polynomial function. Then the second generalizing statement you get to make about graphs of polynomial functions is this. So, I'm going to erase our recall. So if you don't have this in your notes from last video, get it written down now. Okay, so the next statement we get to make is so all graphs of polynomial functions have no sharp turns. What do I mean by this? Well, let's take a look at these two examples. Here we go. This is what I mean by sharp turns. So yet again, this top one is an example of a polynomial graph. Nowhere in the graph is there sharp turns, right? So there are turns. Here's a turn, here's a turn, here's a turn, here's a turn. But all these turns are smooth, is the way we like to describe them. And to just illustrate what do I mean by sharp turns, right here. This bottom one is an example of what I mean by a sharp turn. And that's right there at the origin. And in addition to that, we know what this function right here is, right? This graph represents what function? So again, how do we understand that? Go back to that list of parent functions we should have memorized at this point in the class. And this is the graph that matches up with the function f of x equals absolute value of x. So, what does this mean? This basically means by this understanding of the graphs of polynomial functions, since the function f of absolute value of x, or f of x equals absolute value of x is a sharp turn in its graph, the absolute value function is not a polynomial function. So if you're ever wondering if the absolute value function was a polynomial function, Graphically, we can understand that it is not. All right? It does not meet this generalization of polynomial graphs. It has a sharp turn. So there you go. Those are just some two quick general statements we can make about the graphs of polynomials. So with that in the back of our heads now, let's go ahead and make some further statements about graphs of polynomials. So here's the next generalized statement we can make about the graphs of all polynomial functions. It's in regards to their end behavior. So we now understand that polynomial functions are always continuous, so there's never a break in the graph. We understand there's never a sharp turn in the graph. And in regards to end behavior, we get to make this pretty interesting comment. And that is that the graphs of polynomial functions on the left and the right eventually either fall or rise forever. Now, what is this statement trying to say? What this statement is trying to say is basically this. Consider this random polynomial graph, all right? This is what this statement is making, is that on the left-hand and right-hand side, so I guess let me add that in my wording, graphs of polynomial functions on the left and right hand sides eventually either rise or fall forever. So what this end behavior statement is saying is that if I give you any graph of a polynomial function, what you can observe is this, is that there will be a middle portion to the graph. And that middle portion is right here. There'll be a middle portion. And in that middle portion, some crazy behavior will be happening. It'll be going up, it'll be going down, it'll be doing a bunch of fluctuations if it wants. But here, craziness happens. Now, what's interesting about polynomial functions is that eventually it will hit a point on the left and the right where it stops changing its behavior, where all that craziness just fades away and it starts doing either one of two things. It either falls or it rises forever. It just stops changing its behavior. So at the ends, one behavior is held forever. So, if you just think about it, that is a very interesting comment and observation to make about polynomial functions, is that in the middle they will have some crazy outrageous behavior, doesn't matter what it is, but eventually all that kind of fades away, and on the left hand side and on the right hand side it will either fall or rise forever. It will stick to one behavior and it won't change again. That's a very interesting observation to make about them. Now the question is, the obvious question to ask at this point is, given a polynomial function, how do you understand what it's doing on the left-hand side and the right-hand side? How do you know what it does on its left and right hand sides? Right? So if I give you some random polynomial function, how can you look at that function and be able to tell me very quickly whether it's going to fall on the left, rise on the left, or fall on the right and rise on the right, right? So the answer to that is the leading coefficient test. And that's exactly what we're going to talk about now. Okay, so let's go ahead and discuss the leading coefficient test. And so this is the test. This is the test that lets you determine the end behavior of a graph. Oh, I guess I should be a little more specific. The end behavior of a polynomial function. So this is a pretty useful test, right? Kind of lets you, again, shortcut your way through graphing a polynomial function. So let's go ahead and talk about it. So given some random polynomial function, right, so f of x equals our generic polynomial function, the test breaks into two cases. It breaks into the case when n is odd or when n is even. In other words, when you have an odd degree polynomial or you have an even degree polynomial. Odd degree and then even degree. Right, so just a quick mental review for ourselves. What are the most basic odd and even degree polynomials we can think of? Well, the most trivial odd degree polynomial is kind of a tie between x and x cubed. I would say x cubed for just nonsensical reasons. But then the most trivial even degree polynomial we can think of is x squared. So there you go. We have odd and even degree polynomials. These are the two cases. And then each case is broken down into two further subcases. So before we get into the subcases, let's try to think about what the determining factor for these subcases are. Right? So you had two cases, and the cases differed based off the degree of the polynomial, whether the degree was even or degree was odd. Now each of these are further going to be broken down into two subcases. So just for a quick mental exercise for ourselves, let's kind of stop the video at this point and let's think. So for the two total cases, the determining factor was the degree. What's going to be the determining factor for these subcases? What's the other special part of a polynomial we're usually interested in? So try to pause the video now and give it a quick think. Okay, so the determining factor for our subcases is going to be the leading coefficients. Alright, so each subcase is made off of the leading coefficient. And the first one is when the leading coefficient is positive. So a sub n is greater than 0. And then your second subcase is when the leading coefficient is negative. When a sub n is less than 0. And I've come to the realization I'm going to need more space than what I'm giving myself. So we're going to go ahead and erase this, and we'll just get to things as they naturally come up. So, we'll just consider the first case as a whole when n is odd. When you have an odd degree polynomial, your first subcase is when the leading coefficient is positive. So this means a sub n is greater than 0, and what happens is you get this behavior of your graph. So for the left-hand side, your graph is going to fall forever. And for the right-hand side, your graph is going to rise forever. Okay? What do I mean by that? Quick visual example. I mean something like this. Something like that, right? Here on the left, we are falling. And here on the right, we are rising. So, one key point I want to make about this test is that what have we made a comment about? We have made a comment about the left hand and right hand end behaviors of the graph. So remember I talked about how there's the middle portion, where the middle can do a bunch of crazy things. So what I want to emphasize in this visual example is that my middle is dotted. My middle is dotted, and why is that? Because I have no idea what's happening in the middle of this graph. It may not look like the dotted line I draw. It may look I have no idea how it's going to look because I'm making no comment about the middle region of my graph. I'm only making a comment about what's happening at the left end side and what's happening at the right end side. It's a very important thing to remember about this test, this leading coefficient test, is it's only talking about n behaviors. It makes no comment about the middle region of your graph. So the middle is dotted because I do not know what is happening. What is happening there. That's a very important point about this graph. Always keep that in the back of your heads. This graph is only making comments about n behavior. It's not making a statement about the middle region of the graph. So there's your first subcase. For an odd degree polynomial with a positive leading coefficient, the left shall fall and the right shall rise. That sounds a bit political. But there you go. Now let's consider the second subcase. So go and take a moment, pause the video, and get this copied down. Alright, so the second subcase. So our second subcase is when the leading coefficient is negative. In other words, a sub n is less than 0. So in that case, the behavior flips. Right? So the left-hand side, before it rose, or it fell, so now it's going to rise. And the right-hand side rose, so now it's going to fall. The behavior flips in comparison to the first subcase. This is what happens with that. So, another quick visual example is that this time we're going to get something like this. Alright, so here on the left we are rising. And here on the right we are falling. And again, there is that middle region where I have no idea what's going on because I'm only making a statement about the n behaviors. Okay, now I want to take a further step back to kind of remember, to connect something we've talked about before to this. This idea that the left is going to rise and the right is going to fall shouldn't be too surprising when we understand we're dealing with an odd degree polynomial with negative leading coefficient. So, as a quick aside, let's recall our most basic odd degree polynomial, or x cubed. And we know that the parent function looks like this, right? Now we've talked about translations of graphs at this point, and one of our translations is reflections. So if I want to do minus x cubed, we understand how this changes our graph is it takes the image and it folds it over the x-axis, and so it produces that. And if we take a look here, that's exactly the behavior we're describing here. X cubed is an odd degree polynomial because 3 is odd, and the leading coefficient, which here is 1, is greater than 0, so we are seeing the exact behavior we expect. Our left is falling and our right is rising, and then for the bottom one, when we multiply by a negative 1, again we have an odd degree polynomial, but this time our leading coefficient is negative 1, which is less than 0, and it indeed is rising on the left-hand side and is falling on the right-hand side. So, this whole leading coefficient test, we've actually been doing it through our understanding of translations. We just didn't give it a name. We didn't say this is an actual test you can use, but that's exactly what we're doing now. So that's just a cool quick aside just to show you we've already been using this stuff. Now we're getting a stronger understanding of what we're doing. So again, we're going to go ahead and move on to our second case, the case in which n is even. So at this moment, go ahead and pause the video and copy all this down. Wonderful. So, let's discuss the second case now. So we understand what happens when you're looking at an odd degree polynomial, and its two subcases. Well, let's now consider an even. So what happens when n is even, or you have an even degree polynomial? Well, still the same two types of subcases. Your first subcase is when your leading coefficient is positive. So an is greater than 0. The condition on the subcases won't change, is what we're going to see, is that the two subcases are still when the leading coefficient is positive and the leading coefficient is negative, but the behavior that is described will be changed. So our first subcase with the positive leading coefficients, we get the result that the left-hand side rises and the right-hand side, what is the right-hand side going to do? Well, at this point, I would like you to do this again. Go ahead and give yourself another aside. Oh, let's go ahead and write down another aside. And again, go ahead and consider this. X squared, our most basic even polynomial function. What happens on the left and the right for an x squared graph? Take a moment, think for yourself. Right? So, the x squared makes that parabola, so both the left and the right hand sides rise. Alright, and a quick sketch. We've already talked about it. We have our parabola in our heads, and we understand we expect something like this. Again, no idea what's going on in the middle, but at the very least, on the left and the right, some point we're eventually just going to rise forever. That's exactly what we see with our little aside x squared. We get that parabola U shape. Okay? So that's the first subcase. With a positive leading coefficient, we understand that on the left and on the right hand sides of the polynomial graph, it will be rising together. Now then, let's go ahead and do the second subcase, the negative subcase. And hopefully in your heads, you should be able to already understand and know what the second subcase results will look like. So if I have a negative leading coefficients, so an is less than 0, a sub n is less than 0, what's going to happen on the left and the right hand side? Well, hopefully, and if you should be able to see in your heads. If you can, no worries, no big deal. But what we're going to see is that both the left and the right hand side will fall together. They both fall. So a quick visual example. Will be something like that. Both the left and the right hand sides will fall. Again, no understanding of what's going on in the middle. Now, going back to our quick aside board, right? We understand the x squared graph looks like this, and because we understand how translations work, we also understand how negative x squared looks. It is just an upside down parabola. Right? Again, this shows the exact behavior we're expecting. We have an even degree polynomial, because 2 is even. We have a negative leading coefficient, because -1 is less than 0. And so, as we can see on the left, we are falling, and also on the left, we are falling. Both the left and the right are falling in unison. There you go, the exact behavior we expected to see. Now, this as a whole, oh, I forgot to label this as the second subcase. So these four cases together make up the leading coefficient test, and it's a very quick and easy way to determine what the end behavior of your polynomial graph is expected to be. To make some generalizing statements about it, if you haven't done so already, go ahead and pause the video and copy this down. Okay, so hopefully we can all see that a generalizing statement we can make from this test is that even degree polynomial functions have the same behavior on the left and the rights, and that odd degree polynomials have opposite behavior on the left and the rights. Okay, so with the understanding of the cases of the test now, we can see that these are two statements we can make about polynomial functions. So that's the leading coefficient test. Let's go ahead and try doing a quick example using it. Okay, so let's consider the following example. Let us describe the end behaviors of these three functions. So, for our first function, we have minus x to the fourth plus 6x minus 7. So let's understand its end behavior. Well, first things first, let's identify its degree. And the degree of this function is 4, because 4 is our highest coefficient, or our largest coefficient, 4 is our largest power, and 4 is an even number. Great. So already we understand that whatever the end behavior is for the left and right hand sides, it should be doing the same on both. Now then, let's identify our leading coefficients. And our leading coefficients can be seen quite easily as being -1. And -1 is in fact less than 0. So bringing that all together, we understand that both the left and the right need to fall. Both fall. Okay? And so that's it. When it comes to using the leading coefficient test, it's as straightforward as that. Just identify the proper components and then piece together the information they give you. Moving on to our next example, we have 14 times x to the 7th plus 5x squared plus x. So again, we identify the degree. The degree is 7. 7 is odd. Our leading coefficient is what we need to identify next. And we can see quite easily that is 14, which is greater than 0. So going back to our leading coefficient test, we can easily identify that this is a graph which shall fall on the left and rise on the right. There you go. Now, let's consider our last function. So at this point, go ahead and pause the video, do this example real quick on your own, and we'll come back together and talk about it. So go ahead and pause now. Okay, so, blowing through this one real quick, our degree is 5. Odd. Our leading coefficient is -3, which is less than 0. So we expect the exact opposite behavior of the function from the second function. So we are going to, on the left, we shall rise, and on the right, we shall fall. There you go. This is pretty much all the leading coefficient test is. It's just, again, identifying the proper components and understanding what that information gives you. Simple as that. So, let's go ahead and move on to our next discussion. Okay, so continuing forward, I would like to propose this question. And the question is this: what is the minimum information needed to construct the graph of a polynomial function? Well, the answer to that question is this. The first piece of information we need is the end behavior. We need to know what the end behavior of the graph is. Because as we discussed, we understand that polynomial functions after a certain point have the nice property where on the ends of their graphs they exhibit one behavior only, right? So we need to make sure we understand what the end behavior is. And the second piece of information we're going to need is something we've talked about before in this class. We're going to need the intercepts. When does my graph cross its axis, or axes? As I've said before, understanding the intercepts of a graph is a very key piece of information. Now, what do the intercepts translate to? What's another way of describing intercepts? Intercepts are also known as zeros. So let's go ahead and get to that discussion now. The zeros of polynomials. Oh, so if you feel like it, go and pause the video. Make sure you get this copied down. Okay. So, as a quick recall, let's make sure we all are familiar with what I mean by zeros. I'm pretty sure I've mentioned it before, but just in case I haven't, let's go ahead and restate it. So when I say the word zeros, what I mean, at least in the terms of our math class, is that zeros are the values of x that make f of x equal 0. All right, so quick example. X squared minus 4, if my function is x squared minus 4, then x equals 2 and minus 2 are zeros of the function. All right, so zeros are just the values of x which I can plug into my function, and it makes my function equal 0. Now then, there are some statements we can make about the zeros of polynomial functions. So what are those? So when it comes, just to be nitpicky, when it comes to the real zeros, of polynomial functions, we can make these statements about those. So if x equals a is a zero of the polynomial function f of x, where a is a real number, then we can make these following statements. First and foremost, x equals a is a solution to f of x equals 0. Right? So this is just restating that definition of what it means to be a 0. If you are a 0, then you make the function equal 0. The second statement we get to make is that x equals a is a factor of f of x. Now, this one I do want to point out, so this is a pretty powerful statement. If I have a 0, then that 0 must be a factor of my polynomial function. It's not too important to us today, but in a couple lectures, I think 2 lectures in the future, this statement right here is going to become a backbone of an entire lecture. Is the fact that if I have a 0, then that 0 must be a factor. Just wanted to point it out. It's not going to be majorly relevant today, but will become extremely important a few lectures from now. And then the last statement we can make, and this is the statement that's more relevant to today's lecture, is that if I have a 0, then a comma 0, the point a comma 0 is an intercept on my graph. So this is the important one for us today. So just to restate, when it comes to the real zeros of polynomial functions, and just to reiterate, what is a 0? It's a value of x that when plugged into my function makes the function equal 0. Right? So if I have a 0, then I get to say that that 0 is a factor of the polynomial, and I get to say that the point a comma 0, where a is the value of x, this is an x-intercept on my graph. So here are some generalizing statements we can make in regards to the real zeros of polynomial functions. So go ahead now, pause the video and get this copied down if you haven't done so already. Okay then, well with that out of the way, we're going to talk a bit more about these 0 values. We're going to make it a bit more, we're going to make a couple more statements about them. So let me go ahead and erase all of this. So the things we just listed are nice. They're very useful to know, undoubtedly, but to me, they're not that exciting. Here are the exciting things we can make, or the interesting comments we can make in regards to zeros of polynomial functions. So important notes about zeros for polynomial functions. Alright, so here's the more exciting notes we can make. And the first one is this. A polynomial function of degree n can have at most n zeros. Alright, and so this statement right here is something we've been constantly alluding to in this class, right? When we solved linear equations, how many solutions do we get? 1. The degree of a linear equation is 1. When we solved quadratic equations, what was the max number of solutions we can get? 2. What's the degree of a quadratic? 2, right? That connection we've been forming in the head, that circular argument, how degree always seems to translate into solutions and other things like that. Now we're generalizing it right here. If I have a polynomial of degree n, then at most it can have n zeros, right? So, a very interesting and a very important thing to understand for polynomials. The second note we can make is a polynomial function of degree n can have at most n minus 1 turning points. So a polynomial function of degree n can have at most n minus 1 turning points. What do I mean by turning points? Turning points are relative max and mins. So any polynomial function can have at most n minus 1 relative maximums or minimums. Okay? A quick example, just to illustrate. If we consider x squared, the function f of x equals x squared, right? The degree is 2, so 2 minus 1 is 1. And indeed, if we visualize that parabola, there is 1 relative minimum. We'll only have 1 turning point. 1 relative min. Okay, so here are 2 important notes about zeros. Now we're going to have 1 more important note, so I'm going to need to erase the board. So if you haven't done so already, go ahead and pause the video at this point and get that copied down. Okay, so our last important note about zeros is going to be this. The last important note is going to be this idea of repeated zeros. Okay, so what do I mean by repeated zeros? I mean this idea. X minus a to the power of k, this polynomial function, because that is a polynomial function, this will yield a repeated zero x equals a with multiplicity k. So we're going to introduce a new word there. With multiplicity k. So what do I mean by this multiplicity? All multiplicity translate to into more basic English, stepping away from our crazy math words, is how many copies? So just to reiterate this, if I have the polynomial equation x minus a to the power of k, this will create a repeated zero value of x equals a, in which there will be k copies of this zero. All right? To show a more concrete example of what I'm trying to get at, I mean this. If we consider x minus 1 cubed, right? X minus 1 cubed, this can be rewritten as x minus 1 times x minus 1 times x minus 1. Okay, and so from here we can hopefully see that this will produce x equals 1 and a 0, but there will be 3 separate copies of x equals 1 as a 0. So this has multiplicity 3. So x equals 1 is a 0 with multiplicity 3. So that's what it means for multiplicity. We only see, oh, never mind, ignore that comment. We'll get to that in a bit. But yeah, so just to iterate again, what is multiplicity? So for repeated zeros, or a zero that's produced more than once, so here the zero x equals 1 is produced 3 times, the multiplicity is just that. How many times do you produce that same zero? Okay, now then, let's go ahead and get into a discussion of what it means to graph these repeated zeros, because that's an interesting discussion as well. Okay, so let's quickly talk about what it means to graph these repeated zeros. So if we let x equal a be a repeated zero with multiplicity k, you get 2 possible cases. The first case is this. K is odd. So you have odd multiplicity. So when you're dealing with a zero with odd multiplicity, all that means graphically is that the graph will cross at the point for that zero. So the graph will cross at the point a comma 0. So for a quick visual example, what do I mean by that cross? So if that's the point right there, a comma 0, here's my point, then my graph will simply cross that point. Alright? The graph is cutting through that point. Now, your other type of outcome, your other case, is, well, if one case is odd, then unsurprisingly the second case is when you have even multiplicity. So when k is even, what will the graph do? So graphically, what you'll see is that the graph will bounce at the point. Will bounce at the point a comma 0. So what do I mean by that? So again, there's a. So my point is a comma 0. What do I mean by bounce? I basically just mean this. It hits the point, and instead of crossing the point, it bounces back up. Right? Or the second type of outcome you can get. Or, so let's say there's again. The second type of bounce you can get, so here we come down, we bounce back up. The other type you can get is we're going up, we hit it, and then we bounce back down. So that's what I mean by a bounce. So there you go. When you're graphing these repeated zeros, understanding the multiplicity is very helpful, because if you know the multiplicity at that point, you understand if your graph is crossing at that point or if your graph is bouncing at that point. So that'll be it for our discussion for the zeros of polynomial functions. So let's move on to our next topic of discussion. Okay, so we've talked about and we now understand what the properties of zeros are. Like graphically, when I go to construct my polynomial function, what happens at these zero values? We have a better understanding of that now. So the question still stands is, given a polynomial function, how can I find these zeros? And so for now, the only tool we really have is factoring. That's the only real way we've talked about in this class to determine the zeros of a polynomial function, is to simply factor it, and once we factor it, we go and we solve for x-intercepts. Okay, so that's the only tool we have currently. And in a couple lectures, actually, we're going to discuss some other ways to determine zeros, some more complex methods of factoring, essentially. But before we get to that, since just hardcore factoring is pretty much the only tool we have for the time being, I thought I would go ahead and just mention 2 very helpful factoring techniques that come up often enough that they're worth memorizing. So some helpful factoring techniques. There's 2 of them I want to go ahead and mention at this time. One of them I've seen a lot of you use already, which isn't very surprising. But for those of you who haven't formally seen it, this is the first helpful factoring technique. If you ever see a value like this, where it's one quantity squared subtracted by another quantity squared, so a squared minus b squared, it will always factor in this way. This can be factored into a minus b times a plus b. All right. As I said, I've seen a lot of you use this already, but for those of you who haven't, there you go. This is like the #1 factoring technique, like in my opinion. You use it so often. Now, one that's used not quite as often, but is still just as equally important to know is, well, here we had two values being squared. Let's just go ahead and bump up the power by 1. What happens when I have two values being cubed? And I take the difference of those. Oopsies. So a cubed minus b cubed. Some of you probably, I'd be surprised if any of you know this one, but this also can be easily factored, and how it factors into is in like this. So a cubed minus b cubed factors into a minus b times the quantity a squared plus ab plus b squared. So that's the second helpful factoring technique I want to go ahead and mention for the time being. As I said though, we're actually going to spend, I think 2 or 3 lectures from now, we're actually going to talk about some other more advanced ways of factoring a function and, or factoring polynomial functions, I should say. But for the time being, here are 2 helpful ones that if you haven't been introduced yet, I thought I would go ahead and do so now. Alright, so let's go ahead and just do 2 quick examples with them. So if you haven't done so already, go ahead and pause the video and get these copied down. Okay. So let's go ahead and use these real quick in a quick example. Let's factor x minus 9. And then the second one we'll factor is x cubed minus 27. So, let's go ahead and do the first one. Alright, I have x squared minus 9. And what we all should start getting comfortable with understanding and seeing is that this is the same as x squared minus 3 squared. So right there, this is the exact form we're looking for that helpful factoring tip I just listed. Because here's my a, it's x, and my b is the value 3. So using that technique we just listed, this can easily be factored into x minus 3 times x plus 3. Okay? So hopefully this illustrates why understanding that factoring technique is so important, because it just makes things so much easier for us, and it really speeds up the process of trying to factor certain polynomials. Now, going over and applying that second technique real quick, x cubed minus 27. Now this one's a bit harder to see, but I would still hope people are getting comfortable with and able to see this more easily, is that this is the same as x cubed minus 3 cubed. Okay? And again, this is the exact form we're looking for to use that technique I just listed. So this easily gets factored into x minus 3 times x squared plus 3 times x plus 3 squared. Alright, and then calculating that 3 squared real quick, we get x minus 3 times x squared plus 3x plus 9. So, pretty straightforward examples. Just wanted to list those 2 factoring techniques in case anyone had seen them. And here's how you'd use them in a practical application. Well then, wonderful. Let's go ahead and get back to graphing, because let's do some graphing examples, since that is kind of the big idea for today's lecture. Okay, so at this point we went ahead and we've talked about how things like the degree, the leading coefficient, and the zeros of a polynomial function, how understanding what those are can lead you to understand the behavior of the graph. Alright? So let's go ahead and use all that information we've gathered now and do this example. Let's create a sketch of the function f of x equals x minus 2 squared times x minus 3 to the 5th power times x plus 1. So at this point, with everything we've talked about, we don't have to go through and make a list of tables anymore and just plot a bunch of points. We just need to identify the key pieces of information, that being the degree, the leading coefficient, and the zeros, and use that to construct our graph. So let's start with identifying the zeros of this function. So what are the zeros? So take a moment now and think for yourself and see if you can identify what the zeros are for f of x. Okay, so hopefully at this point we have little to no difficulty seeing that the zeros for this function are 2, 3, and -1. Okay? And if we weren't able to successfully see that, or if we're struggling to identify that, that's not a big deal. It just means we need a bit more practice, and that's okay. Getting a bit of always needing more practice is never a bad thing. So here's how I walk through in my head, just for those of you who are a bit shaky on how we get those. Here's how I walk through my head to identify the zeros. This is my function as a whole, is that whole thing. But what I can see, what I can tell from this, is that I have three distinct equations being multiplied together. Those being x minus 2 squared, my first equation. My second equation is x minus 3 to the 5th power, and my third equation is at x plus 1. Now why is it important for me to see that I have these three values being multiplied together? Because if I'm looking for what makes this thing as a whole, what makes my function as a whole equal 0, and I have three values being multiplied together, through the properties of multiplication, I can understand that when either one of these three equations are 0, the whole equation must be, or the whole function must be equal to 0, right? If I'm multiplying any value by 0, the whole thing becomes 0. So if I can just figure out when either three of these equations equal 0, I will know a 0 for my function as a whole. And so then the game just becomes, when is x plus 1 equal 0? Well, when x equals negative 1. When is x minus 3 to the power of 5 equals 0? Well, when x equals 3. And when does x minus 2 squared equal 0? Well, when x equals 2. So just like that, I can quickly understand what the zeros of my function are. Now, in addition to understanding these zeros, we have a new concept to attach to this, the idea of multiplicity. So let's understand what the multiplicity of these zeros are. Well, for the first 0, let's start with x equals 2. We can understand what the multiplicity is. Right, so take a moment, see if you can identify what the multiplicity of the 0 is. So, we can understand that the multiplicity of this 0 is 2. Why is that? Well, the power attached to that x minus 2 is 2. And remember, multiplicity is just the idea of how many copies do I make? Well, x minus 2 squared implies x minus 2 times x minus 2. So I'm making 2 copies, hence multiplicity of 2. So similarly, for the x equals 3, 0, the multiplicity is 5, because again, we have the x minus 3 to the 5th power. That means we're making 5 copies of x minus 3, multiplicity of 5. And then lastly, for that negative 1, 0, what is the multiplicity there? Well, that's where we go back and we understand there is no power written here, so that means there is a hidden power of 1. So this has multiplicity of 1. And there you go. Just like that, we can easily identify what the multiplicities of our zeros are. So the next piece of information we're probably wanting to know, or we're actually going to need to know, is the degree. What is the degree of my function? Now, to get the degree, right, the degree would be the highest power of my function. In other words, when I multiply all these things together, what is the highest power that's produced? That would be the degree of my function. So, we have to ask ourselves then is, well, do I really have to sit here and multiply out what x minus 2 squared is, then multiply out what x minus 3 to the 5th power is, and then multiply all those bunch of things together? Do I really need to do that? Well, not quite, right? Because all we're concerned about is tracking and understanding what the highest power will be after we do all that multiplication. And we understand that this breaks down into 3 separate equations. So let's just understand what the highest power is produced from each of these equations. So for that first one, x minus 2 squared, hopefully it's not too hard for us to understand that if I was to multiply that out, this x minus 2 squared, the highest power it would produce is an x squared value. Okay? Then moving on to our second equation, I have an x minus 3 to the 5th, and a very similar argument is made in that the highest power that will produce is an x to the 5th of value. And then lastly, for that x plus 1, the highest power there is just that x. So here will be the 3 highest powers produced from each of my equations. And so if I multiply all these together, I'm going to get an x to the So I get an x to the 8th. And so that's how I can easily identify that the degree of my polynomial function is 8. And what's going to be important for us is that we understand this is an even degree. Okay? So that, if that was a bit confusing for you, just rewind back and listen to me again. Hopefully it's a bit clearer on the second run through. If not, and if you still struggle with the idea of identifying easily what the degree of this polynomial function is without having to do all that crazy multiplication, send me an email, set up a Zoom meeting with me, and I'd be more happy to explain it again. But just continue on then. So we now understand that we have a degree 8 polynomial, so that means we're even. Great. What's the last piece of information we're going to need? Well, the leading coefficients is what we're going to need to understand. So what is the value that's going to be attached to our highest degree with the number being multiplied? And again, we don't have to go through and do all the crazy multiplication. Again, if we can just kind of track the highest power in our head, which we've kind of done right here, hopefully we can still see that the highest power, x to the 8th, will have a leading coefficient of 1, which is greater than 0. So that's going to tell us how to properly use our leading coefficient test when we go to graph. So I have a leading coefficient which is positive, in other words. So this is the list of information we're going to need to be able to successfully create a graph of our equation, or of our function. So I need the board space at this point, so if you haven't done so already, go and pause the video to copy this down, and then we're going to move on and go and create the sketch of this graph, or this function. Okay, so let's go ahead and do just that. So then to graph this, we understand we have zeros at the points -1, 0, 2, 0, and 3, 0. In addition to that, we were even degree. Right? So both the left and the rights will either rise or fall together. How do we know if they're rising or falling? Well, the leading coefficient was positive. So we know our end behavior is a rise and a rise. Beautiful. Right? We have a rise and we have a rise. The question is, what's going on in the middle? Well, that's where understanding the multiplicity of your zeros is so important, because I know I will be traveling down to this -1, 0, or this -1, 0 points. And what was the multiplicity at this point? This had odd multiplicity. So I need to cross. Okay? So we understand that as we approach this point, it's going to cross over the axis. Great. So now we need to start traveling to this 0, 2, 0. And again, we understand this had even multiplicity. So we need to bounce. We need to bounce. So after we cross the axes, my graph's going to travel towards that 0. And as it hits that point, it's going to bounce right off. Beautiful. And then again, we need to start traveling towards our last 0. We understand this had odd multiplicity, so we need to cross. So after I bounce, I'm going to start traveling towards this. Then I'm going to connect back up with that end behavior, and there you go. Right? The sketch of this graph, if we were to actually go through and create a super detailed sketch of this function, it would take some general shape like that. This is what we've this is what we can now understand and accomplish using the things we've talked about today. All right, so there's our first example. Go ahead and copy that graph down if you haven't done so already, and we'll move on to our next. Okay, so here will be our next example. So same directions, but new function. And the function we're going to consider this time is x to the 5th plus 6x to the 4th plus 9x cubed. Okay? So this example is going to be the one I want you to do on your own. This is the one I want you guys to do on your own. So go ahead and pause the video and give this one a shot. I'm going to give you a hint, if you can't see it already. But the hint for this is you will need to factor. You'll need to factor this one. So go ahead, try to factor it, work on your own. Go and pause the video now, give this one a shot. And then after you unpause it, I'm just going to go ahead and tell you what the answer I got was. So go ahead and pause it now. Alright, so hopefully you all gave it a shot. And for those of you who did, have an answer to compare. This is the graph I created. So here's the graph I created. I have a odd degree function which is falling on the left, rising on the right. It has two zeros. It has a 0 at -3 and it has a 0 at 0. The -3, 0 has even multiplicity, and the 0 at x equals 0 has odd multiplicity. So this was the function or the graph I created. Hopefully we got it the same thing. If we didn't, never believe I'm correct and you're wrong. Double check your work. I could easily just be as wrong. So call me out, send me an email, and we can compare. Besides that, let's go ahead and move on to our next example. Okay, so for this example, we're going to go ahead and determine the equation of the 5th degree polynomial for the following graph. So essentially, we're going to do the exact opposite of our previous example. The other example, we started with the function and we made the graph. So this time we're going to go the other direction, but we're still going to need to identify the same pieces of information that we used in our previous example. In other words, we're going to need to know what the degree, the leading coefficients, and the zeros are of this function. Well, the degree, easy enough. The problem tells us what the degree is. This is a 5th degree polynomial. We are odd. Okay? Now, using the fact that we know we're odd, we're going to go ahead and talk about the end behavior. All right? So, for the end behavior, I have the left rising, and I have the right falling. So why this is important for us is because if we go back to that leading coefficient test, and we go to the odd degree case, and we look at the subcases, this behavior is indicative of a negative leading coefficient, right? So a negative leading coefficient produces this results. So that's why that's important for us, because now we understand that our negative leading coefficient has to be negative. Or our leading coefficient has to be negative. Great. So now we understand 2 of the 3 pieces of information we need to know. The last one is being the zeros. So let's go ahead and discuss the zeros now. So for us, graphically, zeros are x-intercepts, or essentially points at which we cross the x-axis or we bounce off of the x-axis. And so we can see quite easily there are 3 points that show that behavior for this graph. We have a point in -4, 0, a point at 0, 0, and a point at 3, 0. So our zero values are -4, 0, and 3. Now, just like the previous problem, in addition to knowing the zeros, we also want to understand their multiplicity. So we can understand that since at -4 we are bouncing, this is even multiplicity. At 0 we are crossing, so that is odd multiplicity. And then at 3 again we bounce, so this is again even multiplicity. Beautiful. Okay, so here's the information we're going to need to use in order to construct the equation of this graph. So I'm going to go ahead and erase this portion now, so you haven't done so already. Go ahead and copy this down, pause the video. Okay. So let's get into a discussion about these zeros again. Let's go back and think about what we talked about when we first talked about zeros of polynomial functions. We said that if x equals a is a zero, then it is a solution to the question of when does f of x equal 0. That was the first thing we said. We also said that graphically the point or the value x equals a has to be an x-intercept so it makes the point a comma 0, which is what we have here. And then the third thing we said was that if x equals a is a 0, then x minus a is a factor of your polynomial. Okay, so what this gives us is that we now understand the three factors of our fifth degree polynomial. So we know that whatever f of x may be, whatever the function we're going to create is that it must have these three factors. It must have the factor x plus 4, x minus 3, and x. Because these three factors generate our three zeros. This makes the 0 minus 4, this makes the 0 of 3, and this makes the 0 of 0. So that's the first thing we need to identify, is we construct that through our factors, or through our understanding that zeros make factors. Okay then, now we need to address the multiplicity, okay? We need to address what are the powers, what are the exponents that are going to be attached to these factors. We understand that for the x plus 4, it has to be even multiplicity. So this has to have even power. Same with x minus 3, this has to have even power. And then this value of x has to have odd power. So, needs even power. And this one needs an odd power. But in addition to this, we understand that the degree of the polynomial is 5. So we know that, so I'm going to go ahead, I'm going to call this A, this B, and this C. We know that A plus B plus C has to equal 5. We know that A must be even, B must be even, and C must be odd. Okay, and they have to be positive numbers. And they all must be positive. Alright, wonderful. Now, so at this point it just becomes a matter of doing some nice mental math in our head and trying to some different number combinations. So I would encourage you at this point to pause the video and try to figure out for yourselves what are the values of A, B, and C. What must they be? So go ahead and try pausing the video and thinking about that now. Right? Okay, so if you give it enough, if you give yourself enough time to think about it, you'll eventually come to the conclusion that A and B must be 2 and that C must be 1. This will be the only possible number combination of positive numbers that when added together with these added conditions equal 5. So what that tells us is that going back up to here to our equation, right, x plus 4 needs to be squared, x minus 3 needs to be squared, and then the x can be left by itself because we don't bother writing powers of 1. So there you go. This is how we use the zeros and their multiplicity to construct this portion of our equation. Now the last piece of information, we need to make sure we use everything, right? So we've used the degree. Our powers do add up to 5. Wonderful. We've used the proper zeros. I have the -4, 0, I have the 3, 0, and I have the 0, 0. Great. The last piece of information we haven't used is the leading coefficients. So now we need to make sure we properly use the leading coefficient, and we understand from the end behavior we're looking for a negative leading coefficient. However, if I multiply this current equation out, I'm going to get a positive leading coefficient. So in order to ensure that negative leading coefficients, I need to put that negative out in front. So just to re-emphasize, putting that negative right there, this guarantees a negative leading coefficient. And that's the last thing we have to make sure we do. So there you go. And that is the equation. We don't need to bother multiplying it out. We can leave it like this. But this is the equation for the fifth degree polynomial that has this following graph. That's how we would run through constructing something like that. So go and take a moment now to pause the video and copy all this down, and then we're going to move on to our next example. Okay, so let's go ahead and do our last example for the day. And it'll be the same type of problem, except we're going to change the graph and the degree. So the graph we're going to consider this time is this. We'll consider -3, 2, and 3. There you go. So this will be the graph we consider. Okay? With these points that I've highlighted being -3, 2, and 3. So let's do the same type of problem, but this time we're going to do a 4th degree polynomial with this following graph. Let us construct the equation for this graph. And again, I would like you to try working on this one on your own, so go ahead and pause the video and try figuring it out. And after you unpause, I'm going to simply write my answer, and then hopefully we'll get the same answer. We'll compare. So go ahead and pause the video now. Okay, so the answer that I got, and please check your own work with mine. If you get a different answer from me, don't automatically assume that I'm right and you're wrong. Double check your work. I could have made a mistake. But this is the function that I got. Let me write it down right here. So I got f of x equals x plus 3, x minus 2 squared, x minus 3. So this is the function for f of x that I got. Go ahead and compare it with your own answer. Hopefully you got the same thing. If not, double check your work and send me an email. But besides that, that's it for today's lecture, everyone. Hope everyone is having a nice time in quarantine, keeping those spirits up, keeping yourselves healthy and clean. And I'll catch you guys in the next video. Have a nice day, everyone.